Hello, I will now begin the presentation for the AlphaContol team, led by Professor Kim Hakil from the Alpha project. The order of presentation is as follows. After introducing the team, the theories we learned and the test video implemented with Mirai are prepared. I'll wrap up the presentation with feedback. Our team's goal is to implement and optimize PID, control, and pure pursuit using a simulator. Following our study of autonomous driving theory, the introduction of team members is as follows. The entire course of the project, our team implemented the learned theory as Mirai by adjusting the coefficients of the PID and pure pursuit controls. We derive the most stable values. MPC is Model Predictive Control, a control algorithm that solves optimization problems by modeling systems and predicting future behavior. This allows you to take into account the state of the system to determine the optimal control input and achieve your desired goals. PID control stands for Proportional Integral Derivative Control. Measure the output of the control target and calculate the error by comparing it to the desired setting value. Calculates the amount of adjustment required for control based on the error value. PID control consists of three components. The P term adjusts the control input relative to the error. The larger the error, the greater the amount of change in the control input, which helps to reduce the error quickly. However, with only proportional control, the error does not converge to zero, and the system may not be stable. Paragraph I adjusts the control input by integrating the cumulative value of the error. This helps to stabilize the system if the error occurs for a long time. Integral control produces a control input proportional to the sum of the errors. So even if the error is zero, a constant control input can be maintained. Paragraph D adjusts the control input in proportion to the rate of change in the error. This improves the response rate of the system by detecting the rate of change in error, predicting future error trends, and adjusting control inputs. Differential control can reduce overshooting or vibration. Pure pursuit is a path-following algorithm used by robots or autonomous vehicles to track and reach their target points. The algorithm is based on the current and target positions of the robot or vehicle and determines the next target point to generate a control input. The pure pursuit algorithm is a path-following algorithm that runs fast and smoothly along the path. Exceeding paths can cause vibration, and large curvature in corners can cause difficulty in tracking the path accurately. It may not follow the target path exactly, but it is mainly used for smooth driving. The Stanley method uses the curvature of the lane you want to follow and the lateral error to control the steering angle of the vehicle. Plan our journey based on information. Apply the control algorithm Pure Pursuit to track your target point and drive safely. Pure pursuit is a path-following algorithm that tracks paths along target points. Stanley is an autonomous vehicle system that extends pure pursuit to follow the route, bringing it closer to the route and minimizing errors. It's using Mirai Simulator. You can choose the route and type of vehicle, and you can implement autonomous driving through the code after connecting to RUS communication. It took a lot of time because the setting process for executing Mirai was complicated. The following is a total of 9 cases, and the speed and acceleration data of 3 unstable cases. As mentioned earlier, these are cases in which I gain and P gain values have been changed. If you look at the graph, it looks quite unstable. This is a test video. All 3 cases show unstable appearance. The following are the most stable driving cases among the 9 cases. By further lowering the d-gain value, it is possible to maintain a stable max velocity value and control overshooting stably. This is a test video. It shows a much more stable driving than other cases. In the PID settings is 9 cases, the LFD coefficient was compared with 1 and 10. When the LFD is 1, it shows stable steering control in the curved path. However, when the LFD was 10, as the target distance increased, it deviated from the path and showed a larger steering. This is a test video. Through the test, we were able to confirm the theory we learned. Here are the feedback and future plans. Our team wants to study autonomous driving more deeply with the following feedback and plans. This has been AlphaContol team's presentation. Thank you for watching the presentation.